CLASSE is a center at Cornell that does a wide range of research. We look at the early universe using collisions at the Large Hadron Collider. We study astrophysics. We are the home of CHESS, which is an X-ray user facility and serves hundreds, even thousands of scientists every year. It seems like a very diverse collection of studies, but in fact there's one unifying principle, which is all of them rely on beams of one kind or another. It can be gravitational waves or light from the universe. It can be X-rays or beams of electrons or protons here on Earth. And so beams turn out to be our unifying theme, and in addition to using all those beams to learn about nature, we also learn about beams themselves. We want to make beams that are intense, that are well focused, and we learn about the phenomena that are barriers to that. We overcome those barriers to make more intense, more powerful beams. And those beams can be used for an incredibly wide variety of scientific purposes.
So I work on a proposed upgrade for the CESAR storage ring. And the idea is that we will increase the energy and the flux and the intensity of the X-rays for all of our CHESS users here.
CHESS is one of 2 high-energy X-ray sources in the country. Scientists come from all over the world, about 1,300 each year. They stay for anywhere from a day to a week, using the X-ray beams to collect data about their scientific subjects. So on the one hand, we study materials, for example, questions like what's going on when a metal begins to stress and fracture. We also can use these very high-energy X-rays to look at materials at all different length structures at the same time, and we have unique detectors that enable that. So you can look at a superstructure in a material and at the same time zero in on the atomic scale.
So CESAR is kind of unique in that it is actually 2 counter-rotating beams rather than just a single beam. These beams are separated by a few tens of millimeters. And this poses lots of challenges and limitations to what we can do. The reason we store 2 counter-rotating beams is actually for historical reasons, when CHESS used to run concurrently with high-energy physics collisions. So unfortunately, this limits the quality of the beam, namely in the size of the source and in the lifetime of the source. So basically how many photons per second we can produce for users. So the plan is that we will actually remove 1/6 of the storage ring, the entire area that contains user beam lines, and we'll replace that with a new magnet structure. This will allow us to go to a single beam that's on axis. It will decrease the source size. It will increase the number of photons per second that we can produce, and at the same time, the CHESS beamline scientists will be designing brand new world-class beamlines as well.
We are also trying to invent an entirely new kind of an accelerator that was first conceived actually in the mid-60s here at Cornell. It's called an energy recovery LINAC, and what it does is combine the best features of the circular accelerator and the linear accelerator. So what do I mean by that? A circular accelerator has the great advantage that the beam passes by over and over again. You can use the same beam accelerated to the speed of light repeatedly. That's an extremely energy efficient way to go. The linear accelerator has the huge advantage that you can produce the tiniest, most intense beam and preserve that intensity and focus from the point of production to the point where it's used.
I started working at CHESS, Mac Chess specifically, about 2.5 years ago. I started with the SRCCS program, which is Summer Research Experience for Community College Students. It was the summer before I transferred into Cornell, and I was working on a microfluidics project. Had never done any material science or any physics, so I was coming from a biochemistry background, but I sent them my transcript and Laura was like, "You're perfect. and I filled the last spot. One of the things that I love most about working here is everyone has their own areas of expertise. So even as an undergraduate coming in with no experience in physics, no experience in microfluidics, I always knew that I could ask questions and ask who would know this.
We are super excited about a new thing called the Center for Bright Beams that is starting. It's located here at Cornell, but with 9 other universities and 3 national labs joining us. And the goal of the center is to invent new strategies that will allow brighter beams for science, for industry. The way we're going to do it is by joining forces of a very diverse team of scientists. So not only we'll have accelerator scientists who study beams as their day job, but we'll also bring in chemists, material scientists, mathematicians, who will bring their own expertise to overcome the barriers to bright beams that exist today. CLASSE, primarily through the CHESS X-ray source, has a very strong outreach program that reaches literally thousands of members of the public every year. School kids come here and do activities. We go out to the schools and out to the community and try and show kids the excitement that is science. There's so many cool things you can do, and it's so much fun to see that spark of curiosity that children have. On the industrial side, the semiconductor industry is a huge user of beams in manufacturing and quality control. We can use them for border security by X-raying trucks that are coming into the country. And then we can use them for scientific research. And here we're talking about brighter X-ray beams to understand the structure of materials and of proteins. Or we're talking about brighter beams, for example, at the Large Hadron Collider, so that we can more likely discover the dark matter that fills the universe. Or we can use them at an accelerator like an electron-ion collider where we will be able to look even deeper inside the proton. Right now there are an enormous number of unanswered questions. We don't know what the dark matter is. We don't know why the universe is made out of matter rather than antimatter. We don't know how gravity works with the quantum universe. And so we strive to understand all of these things. We have a great many tools at our disposal. We use large colliders like the Large Hadron Collider. We use small experiments that measure very detailed quantities, but with incredible precision. And then, of course, we look directly up into the sky.